My name is Sophia Lopez, and I wanted to ask you, do you know what an X-ray is? Well, it is an invisible radiation that is able to go through the tissues and reach elements such as an image receptor and produce diagnostic images. So a lot of people are wondering how this radiation is obtained. Well, today I will be explaining to you all two ways that X-rays are produced, and that's through Bremsstrahlung, which is this one right here, and characteristic. And right here we have our X-ray tube. Basically, to produce an X-ray photon, it is required a vacuum X-ray tube that is composed of a cathode assembly and an anode assembly. The cathode assembly contains a focusing cup and the filament, which is made of tungsten element that is chosen because the high atomic number, high melting point, and high heat conductibility. And more important, the filament produces electrons by thermoionic emission, which I can show you right here. Here's the heated filament. These are the scattered electrons, which is also called boiling off. And this is the process of the heating filament. And this is your electron cloud. These electrons travel at a high speed, approximately half the speed of light, that cross to the anode target. As I show you in this video, the electrons exiting the focusing cup towards the target, and two possible interactions may happen: Bremsstrahlung and characteristics. All of these are the electrons, and that's how it's produced. And this is the X-ray photons exiting, and this interaction right here that you're seeing is Bremsstrahlung. Bremsstrahlung is when high-speed electrons travel to the nuclear force field, which is positive, and the electron is negative, producing an electrostatic force. When the electron is closer to the nucleus, a short wavelength is produced, which is a high-energy photon. If the electron is away from the nucleus, a long wavelength is produced, or also known as low photon energy. Bremsstrahlung means stopped radiation. So this is actually related to the actions of the incoming electron that is braked and deaccelerated and produces the X-ray photon. So the energy of this X-ray photon is exactly the difference between the incoming electron minus the exiting kinetic energy of the same electron. For example, if the incoming energy of the electron is 100 keV and is braked or stopped, and this electron is exiting with 10 keV, the X-ray photon energy is a total of 90 keV. Characteristic interaction, also known as K-shell X-ray production. It happens when the incoming electron has an energy greater than 70 keV. This is required because the binding energy of the K-shell tungsten element is 69.5 keV. So when the incoming electron gets to the K-shell, ejects this K-shell electron, leaving a vacancy on the shell, and gives the opportunity to the other electrons in the other shells to jump and fill this vacancy, releasing the X-ray photons. The energy of this X-ray photon is the difference between the binding energy of the tungsten element, for example, is the binding energy of the M shell, which is, it would be 3 keV, and the X-ray photon should be 69.5 for the K shell. So 69.5 minus 3 keV from the M shell would equals to 66.5 keV. Now I'm going to establish the difference between the two interactions. Remember this, there is a great difference between characteristic and Bremsstrahlung. Once again, characteristic radiation occurs because the kinetic energy of the bombarding electrons is now high enough to eject electrons from the internal shells of the target tungsten atom. As a result of the ejection of these electrons, the atom is in an excited state and has become ionized. The empty place left by the ejected electron is then occupied by an electron by an upper shell, causing the emission of a quantum of X radiation. In this way, the atom returns to its original condition. In the following diagram of the tungsten atom, we got an electron exiting the filament with 70 keV, getting into the inner shell and eject the electron, leaving a vacancy, so the electrons from the other shells, such as L and M, has the opportunity to jump into a higher state shell and fill this shell and release the X-ray photon energy. This process is called the metastable state. So consequently, the create cascade effect because the other shell electrons start to jump into higher energy shells. So the energy of these X-ray photons is the difference between binding energies. This is characteristic. In this diagram, we have the filament with electrons with the same energy, as you can see, 100 keV. For example, electron number 1 gets close to the nuclear force field and is braked or stopped, releasing the X-ray photon, and the incoming electron is exiting with less energy, around 20 keV. So the difference between the incoming electron and exiting electron creates the X-ray photon energy. As the electron gets close to the nuclear force field, the exiting kinetic energy of this electron is going to be less, and the energy of the X-ray photon is increased. And the last electron I'm going to be showing you now, for example, number 3, gets to the middle of the nucleus, so this second one right here goes right here close, and then it exits, but it's closer like that. And then the third one comes in here, hits the nucleus, and the electron does not exit. So the energy of the X-ray photon is 100% of the incoming energy of the electron. This is bremsstrahlung. X-ray tubes produce X-ray photons by sending high-speed electrons from the cathode to the anode. As the electrons hit the anode, their kinetic energy is converted to X-ray energy. The most common type of electron-anode interaction is the bremsstrahlung interaction. Bremsstrahlung's the German word for braking or slowing radiation. It may also be referred to as Brems radiation, and it is produced when projectile electrons are slowed down in the anode due to the electrostatic attraction between the electron and the nucleus. The electron is deviated from its straight line path. As it turns, it decelerates or slows down this change in kinetic energy, resulting in an X-ray photon being produced equal in energy to the amount of kinetic energy lost. This satisfies the law of conservation of energy. For example, bremsstrahlung interactions are responsible for producing a wide variety of X-ray photon energies because electrons may approach the nuclear field at different angles and speeds. Different energy levels of photons will result when an electron is not decelerated to as great a degree due to less sharp than a lower energy photon is produced. Note, the lower the frequency and longer wavelength of this bremsstrahlung photon, in the case of this electron, it has been deviated greatly from its original path, causing it to slow down even further because this electron has experienced the greatest change in its kinetic energy than the previous two electrons. It produces a photon with even greater energy than before, as seen by its increasing frequency and decreased wavelength. 90% of the X-ray produced in the X-ray tube are due to bremsstrahlung interactions because of the wide variety of energies produced as a result of this process. Brems radiation is responsible for the heterogeneous nature of the X-ray beam. As I show you this full video, I want to show you the whole video so you can see the whole interaction. And to conclude, that is everything you all need to know about the bremsstrahlung interaction and the characteristic interaction. That is X-ray production.